Imagine two twins living side by side. One stays on Earth, while the other embarks on a spaceship journey that takes him to the stars at near light speed. When he finally returns, something unexpected awaits. He's younger than his sibling. That's the strange, mind-bending reality of the twin paradox, where time itself bends and shifts depending on how fast you move. It sounds like science fiction, but it's a real consequence of Einstein's theory of relativity. In this video, we're diving into how motion can make time flow differently, revealing a universe where your clock might run slow or fast, all depending on how you move through space. Stick around, because understanding this isn't just about physics. It's about how the fabric of reality could be shaped by motion itself. Understanding time and relativity. In the realm of physics, Einstein's theory of relativity fundamentally shifts our understanding of time from a fixed, universal ticking clock to a flexible, relative phenomenon. Unlike the intuitive idea that time flows at the same rate everywhere, relativity reveals that time can stretch, slow down, or even appear to stand still, depending on the observer's motion. At its core, this idea hinges on the principle that the speed of light remains constant for all observers, regardless of their motion. This constancy leads to some surprising consequences, like time dilation, which is vividly demonstrated by the twin paradox. Visualizing time dilation can be challenging, but imagining it as a kind of cosmic stretching can help. When an object moves at speeds approaching the speed of light, the clock attached to it ticks more slowly compared to a stationary observer's clock. For example, if one twin embarks on a high-speed space journey while the other remains on Earth, the traveling twin's clock will lag behind the stay-at-home twin's clock. Upon returning, the traveling twin will be younger than their sibling, despite both experiencing time passing in a perfectly normal manner on their own journeys. This isn't just theoretical. Particle accelerators routinely observe such effects, where particles moving at near-light speeds decay more slowly than their stationary counterparts, confirming the reality of time dilation. The mathematics behind these effects relies on the Lorentz transformation equations, which describe how measurements of time and space change between different frames of reference in relative motion. Instead of absolute measures, everything becomes relative, depending on each observer's velocity. When visualized, it's as if each person lives in their own personal space-time grid, where the geometry shifts based on their acceleration or velocity. The faster one moves, the more their experience of time diverges from that of those who are stationary or moving more slowly. This interweaving of space and time creates a four-dimensional fabric that twists and curves, revealing realities that are counterintuitive but experimentally validated. In everyday life, these relativistic effects are negligible because most of us move at everyday speeds far below that of light. Still, GPS satellites, which orbit Earth at high speeds, must account for both special and general relativity to provide accurate positioning. Without these corrections, your smartphone's navigation would quickly become unreliable. The twin paradox exemplifies how profoundly our intuitive grasp of time can be challenged when encountering extreme conditions of motion. It underscores that time is not an absolute, universal clock, but a dynamic feature of the universe, one that reveals its true nature only when pushed to the limits of velocity and gravity. The concept of the twin paradox. In the realm of Einstein's theory of relativity, the twin paradox emerges as a fascinating puzzle that challenges our intuitive understanding of time. At its core, it involves two identical twins. One remains on Earth while the other embarks on a high-speed space journey. Due to the effects of special relativity, time doesn't pass equally for both twins. When the traveling twin returns, they're younger than their sibling who stayed behind, despite both twins aging normally in their own frames of reference. This concept starkly illustrates that time is not an absolute universal ticking clock, but is influenced by the motion of observers. The key to understanding this paradox is grasping the phenomenon of time dilation. When someone travels at speeds approaching that of light, their biological clock effectively slows down relative to a stationary observer. This isn't just theory. It's backed by countless experiments involving particles moving at near-light speeds and precise atomic clocks flown in airplanes. For instance, when the traveling twin accelerates and decelerates during their journey, they experience less passage of time compared to their sibling at rest. Contrary to initial intuition, the twin who accelerates and changes direction, thus breaking the symmetry, ages less, and this shift in aging reflects the asymmetric experience of motion. Visualizing this scenario helps. Picture the twins at the start, both synchronized in age. The traveling twins' journey involves high-speed travel through space, then a turnaround and a return. During the outbound and inbound legs, their clocks run slower from the Earth's frame of reference. The acceleration at the turnaround point is critical. It's a non-inertial phase that differentiates the traveling twins' experience from the stay-at-home twins. When they reunite, the math from special relativity confirms the traveling twin has aged less. This is not due to any inconsistency in physics, but arises because the scenario involves different reference frames and the effects of acceleration, which impact the measurement of time itself. The paradox's intrigue lies in how it contradicts usual notions of absolute aging. Our everyday experience suggests that time flows equally for everyone, regardless of motion. Yet, at velocities approaching the speed of light, the reality is starkly different. The twin who ventures into space at relativistic speeds operates on a different clock than the one on Earth. This distinctive influence of motion on the passage of time exemplifies the profundity of relativity, challenging the idea that time is a fixed background and revealing it to be intertwined with the fabric of space and velocity. The twin paradox, therefore, isn't just a thought experiment. It encapsulates the weird, fascinating nature of the universe at the extremes of speed. The role of speed in time dilation. Speed is the key driver of time dilation in Einstein's theory of relativity, and understanding this relationship reveals why time appears to slow down for objects moving at high velocities. As an object accelerates closer to the speed of light, the fabric of space-time warps in such a way that time itself stretches out for that object relative to a stationary observer. Think of it as traveling along a highway. The faster you go, the more your clock falls behind compared to what someone parked on the side would observe. This isn't just a theoretical idea. Scientific experiments with particles have demonstrated that subatomic particles moving at very high speeds decay more slowly than their slower counterparts, confirming that their internal clocks run slower as their speed increases. Visualizing this phenomenon can be conceptually challenging but immensely helpful. When tackling time dilation, imagine two twins. One remains on Earth while the other boards a spaceship that accelerates to a significant fraction of the speed of light. The twin on the spaceship experiences less time passing due to the spaceship's rapid velocity. From the perspective of the Earthbound twin, the traveling twin's clock ticks more slowly. Conversely, from a spaceship's perspective, it's the Earth that appears to be moving, so they see Earth's clock running slow. This reciprocal view emphasizes the relativity of simultaneity, a cornerstone concept illustrating how motion affects measurements of time and events differently depending on frames of reference. At the heart of this effect lies the Lorentz factor, a mathematical expression that quantifies how much time dilation occurs at a given speed. As an object's velocity approaches the speed of light, this factor increases exponentially, making the difference in elapsed time more pronounced. For example, at 90% of the speed of light, time dilates such that a clock on the fast-moving spaceship could appear to run nearly twice as slow compared to a stationary clock. If someone were able to sustain such speed for a prolonged period, they would age noticeably less than someone remaining stationary. This concept has profound implications for hypothetical future space travel or understanding extreme astrophysical phenomena like black holes, where objects routinely approach these enormous velocities. The role of speed in time dilation isn't just about distant science fiction. It has practical effects observable behind the scenes of everyday technology. GPS satellites, for instance, constantly compensate for the effects of both gravity and their high speeds relative to ground-based stations to keep navigation accurate. Without these adjustments, directly linked to relativistic effects, the system would quickly become unreliable. The fact that modern science must account for how speed alters time affirms how deeply woven the concept is into the workings of the universe. It underscores that velocity isn't just a measure of how fast something moves, but a key influence on the very nature of temporal experience itself. The effect of acceleration and deceleration. Acceleration and deceleration introduce a fascinating twist to how time behaves concerning moving observers. Unlike constant velocity, which results in a steady and predictable time dilation, changing speeds significantly complicate the picture. When a spacecraft accelerates away from Earth, it doesn't just increase its velocity, it effectively shifts the rate at which time flows for those on board compared to the stationary or less accelerating observers. This isn't a simple matter of speed alone. The act of accelerating stretches and contracts the fabric of space-time, leading to real differences in elapsed time. Think of acceleration as a kind of forcing function for time dilation. During periods of acceleration, the spacecraft's frame of reference is continuously changing, meaning the effects of special relativity are in a constant state of flux. Visualize a spaceship accelerating away from Earth. As its velocity increases, so does the disparity in experienced time, with the crew aging more slowly relative to the planet. However, it's crucial to understand that during acceleration, the ship's frame isn't inertial, meaning Newtonian intuition of smooth, uniform motion doesn't apply. The acceleration period is when the most significant perception of elapsed time difference occurs, especially when considering the twin paradox scenario. Deceleration acts similarly, but in reverse. When the spaceship slows down, the relative motion between the ship and Earth decreases. Yet, during this phase, the crew's frame of reference is still non-inertial, and the effects of acceleration are still manifest. Interestingly, from the perspective of the astronauts, the deceleration phase often appears as a kind of catch-up, where the aging process accelerates relative to the stationary twin. This phase can be visualized as the space-time fabric bending back into a state that aligns the ship's frame with Earth's, making the accumulated difference in proper time more pronounced over the journey's duration. Crucially, the moments of acceleration and deceleration are what distinguish real-world scenarios from idealized, uniform motion. They reveal that the experience of time depends not just on velocity, but significantly on how that velocity changes. Accelerations are like cosmic markers that record how movement through space-time affects aging, marking the bridge between the theoretical elegance of relativity and practical, observable phenomena. In essence, they serve as the engine that intensifies the time difference, making the twin paradox a tangible demonstration of how motion and gravity, closely linked in Einstein's universe, alter the very flow of time itself. The thought experiment: Earth twin versus space twin. The core of the twin paradox revolves around a simple yet mind-bending idea. Two twins start out together on Earth. One stays behind, anchored in the steady flow of time here on the planet. The other embarks on a journey into space, traveling at speeds approaching that of light. When the spacefaring twin returns, they find their earthbound sibling has aged much more than they have. This seems counterintuitive at first because, from the perspective of either twin, each sees the other as moving. So where does the difference in aging come from? The trick lies in the fact that the traveling twins' frame of reference is not symmetrical. Their experience of time is altered by their acceleration and high velocity during their journey, unlike the stay-at-home twin, whose frame remains inertial. In this thought experiment, the key factor is Einstein's theory of special relativity, which teaches us that time isn't absolute, but depends on the relative motion of observers. When the space twin accelerates to leave Earth, their frame of reference becomes non-inertial, meaning they aren't just moving at a constant velocity, but are changing speed and direction. During the high-speed voyage, time dilation kicks in strongly, causing their biological clock to slow down relative to the Earth twin's clock. This slowdown is predictable and calculable. At speeds close to the speed of light, time on the spacecraft passes at a fraction of the rate it does on Earth. The faster the vacationing twin travels, the more they will jump ahead in age upon return, compared to the twin who stayed behind. Visualizing this helps make the effect clearer. Picture Earth as a fixed point in space, with time flowing steadily from our perspective. Now, imagine the space twin's spaceship, a blur zipping away at incredible speeds. From Earth's point of view, the spaceship's clock runs slow. But on the spaceship, everything feels normal. That twin perceives their own clock ticking normally because all their measurements are relative to themselves. This is the core of relativity. Each twin perceives their own passage of time as unaltered. It's only when they reunite and compare clocks that the discrepancy becomes obvious. Their differences in aging are real and measurable, and it all hinges on the fact that one twin's frame of reference has undergone acceleration and deceleration, breaking the symmetry that might seem obvious at first glance. The real astrophysical insight here is that the paradox isn't a paradox at all when you account for the acceleration phases and non-inertial motion. The twin who travels at near-light speed and returns is not simply moving relative to the Earth twin. It's that their entire frame of reference, including their inertial frames during the turnaround, is fundamentally different. If both twins remained inertial during the entire period, that is, if neither accelerated, their clocks would stay synchronized forever, and no age difference would emerge. But because the traveling twin's course involves turning around to come back, involving acceleration, the two twins' clocks diverge. The result is a stunning demonstration of how the universe's fabric, space and time, are intricately linked and flexible, shaping the very essence of how we understand aging and motion at fundamental levels. Journey of the Traveling Twin. The journey of the traveling twin offers a vivid window into the strange and fascinating world of relativity, where familiarity of time melting away challenges intuition. When a twin embarks on a high-speed space voyage, their experience of time diverges dramatically from that of their Earth-bound sibling. The core principle at work is time dilation, which posits that time passes more slowly for objects moving at speeds close to that of light, compared to objects at rest or moving slowly. For the twin in space, moving at a significant fraction of the speed of light, every day they spend traveling is less than a day experienced by the twin remaining on Earth. Picture a twin setting off on a spacecraft, accelerating to a velocity where relativistic effects become prominent. As they hurtle through space, time for them seems to proceed normally, the clock on their wrist ticking steadily, their biological processes unfolding like usual. Meanwhile, back on Earth, clocks are ticking faster relative to the spaceship's frame of reference. If the astronaut twins' journey lasts a few years from their perspective, decades might pass for the sibling left behind. This creates a stark contrast. One twin ages noticeably less, having experienced fewer moments of biological and physical change. They are effectively frozen in a different timeline, despite experiencing their own personal universe that seems normal and unchanging. Visualizing this disconnect can be even more striking during the turnaround phase of the journey. The traveling twin must decelerate, reverse direction, and accelerate back toward Earth, an incredibly demanding feat, demanding massive amounts of energy. During this phase, their frame of reference changes dramatically, creating a jump in perceived time passing for the twin left on Earth. When reunited, it appears almost surreal. The twin who traveled at relativistic speeds has aged far less, sometimes just a few years, while their sibling has celebrated many more birthdays. The twin paradox, which initially sounds like a logical contradiction, is resolved once you account for acceleration and changing frames of reference, factors that break the symmetry of the situation. This scenario isn't just a fanciful science fiction idea. It's a genuine consequence of Einstein's theory of special relativity, which has been experimentally confirmed with precise atomic clocks flown on jets and satellites. The practical implications extend into modern technology, guiding the calibration of GPS satellites that must account for both Earth's gravity and their orbital velocities. The journey of the traveling twin, therefore, isn't just a thought experiment, but a tangible illustration of how the universe operates on a cosmic level. bending the ordinary flow of time into something more exotic when approached at high velocities. The paradox challenges perception, forcing humanity to rethink reality, illustrating that time isn't an absolute ticking clock, but a flexible, relative phenomenon hinged on motion and gravity. The science behind time dilation. Time dilation stems from Einstein's theory of relativity, fundamentally altering how we understand the flow of time itself. Instead of absolute, universally ticking clocks, time becomes flexible, bending, and stretching depending on relative motion and gravity. The core principle is that when one object moves at velocities approaching the speed of light compared to another, time for the moving object slows down relative to the stationary one. This isn't just a theoretical concept. It has practical implications, observable through precise experiments and technological applications like GPS satellites, which must account for both special and general relativistic effects to maintain accuracy. Visualizing this, imagine two synchronized clocks, one on Earth and another on a spaceship accelerating towards a significant fraction of light speed. As the spaceship speeds up, the crew's perception of time continues normally, but an outside observer would see those onboard clocks ticking very, very slowly. When the spaceship decelerates and reunites with Earth, the spaceship crew would have aged less than those remaining grounded. This illustrates the counterintuitive but experimentally verified fact that motion at high velocities causes a measurable slowdown in the passage of time. The effect becomes more profound as speed increases, approaching the speed of light, where time effectively nearly stops for the traveler. Mathematically, time dilation in special relativity is expressed by a factor called the Lorentz factor, which depends on velocity. As velocity approaches the speed of light, this factor increases dramatically, making the difference in aging or elapsed time substantial over long durations or at extremely high speeds. For example, if a spaceship traveled at 99.9% of light speed for what felt like a year to its occupants, Earth's clocks would show decades passing. This principle isn't just theoretical. It influences how scientists understand phenomena in high-energy astrophysics, like particles and accelerators that decay more slowly when moving at relativistic speeds, or the behavior of cosmic rays zipping through space. In essence, the science of time dilation exposes the universe's underlying interconnected nature, how space and time are woven into a single fabric affected by speed and gravity. It challenges our intuition gained from everyday life, where time feels steady and universal. Instead, it reveals that the universe's ticking clock depends on the observer's motion and position in a gravitational field. Real-world applications, like GPS, must correct for these relativistic effects to provide accurate positioning data, affirming that time dilation isn't just an esoteric idea, but a fundamental aspect of how our universe functions. How special relativity explains the paradox. Special relativity revolutionized our understanding of space and time, introducing the idea that they are woven into a single fabric called space-time. At its core, it reveals that the measurements of time and distance are not absolute, but depend on the observer's motion. When considering the twin paradox, this principle becomes essential. The paradox involves one twin taking a journey at a significant fraction of the speed of light, while the other remains on Earth. Upon return, the traveling twin is younger than the stay-at-home twin. The key to understanding this lies in how relativity describes time dilation, an effect where a clock moving at high speeds runs slower relative to a stationary observer. In the realm of special relativity, the idea is that the passage of time slows down for an object in motion compared to one at rest, from the perspective of an observer. What's particularly captivating is that this isn't just a matter of perception. It's a real physical difference. As the spaceship accelerates to near light speeds, its onboard clock ticks more slowly relative to Earth's clock. This phenomenon can be visualized by imagining a clock on a high-speed train compared to a stationary platform clock. When the train whizzes by at tremendous speeds, the train's clock appears to tick more slowly from the platform's viewpoint, and vice versa. This reciprocal effect is symmetric if both are considered in isolation. But the twist comes during acceleration phases, which break the symmetry and clarify why the traveling twin ages less. The core mathematical insight behind this involves the Lorentz transformations, which relate the measurements of space and time between different inertial frames moving at constant velocities relative to each other. These transformations show that the time interval between events, like tick marks on a clock, depends on the relative velocity. The faster one moves, the greater the time dilation effect. For the traveling twin, the journey involves high-speed travel, but it also includes acceleration and deceleration phases, which are best understood as changing inertial frames. This complexity is what resolves the paradox. The traveling twin's frame is not symmetric during the entire trip. The acceleration phases generate an asymmetry so that, upon reunion, the calculation using special relativity shows that the traveling twin has experienced less passage of time. Ultimately, the paradox dissolves once the entire journey, including acceleration, is considered. Special relativity explains that the twin who undergoes the high-speed trip experiences less elapsed proper time, due to time dilation, during the phases where their spacecraft is moving at relativistic speeds. The difference is not just apparent, but physically real. Clocks on the spaceship genuinely record less time passing. This demonstrates the principle that motion affects time itself. The twin who stayed on Earth aged more, simply because their frame of reference was inertial and less subject to the high velocities that cause time to stretch out. The entire phenomenon underscores how deeply intertwined space and time are, with the relative motion precisely determining who ages less during such high-speed journeys. The impact of general relativity and gravity. Gravity, according to Einstein's general relativity, is not merely a force pulling objects together, but a curvature of space-time caused by mass and energy. When a massive object like a star or black hole warps the fabric of space-time around it, it influences the flow of time in its vicinity. Clocks placed closer to such a mass run slower compared to clocks further away, because the intense gravitational field dilates time. This effect is known as gravitational time dilation. For example, GPS satellites orbiting Earth have to correct for both special and general relativistic effects because their clocks tick slightly faster relative to ground-based clocks, since they are farther from Earth's massive center. In the context of the twin paradox, gravity adds a fascinating layer of complexity. The twin who takes a journey into a region with a strong gravitational field, perhaps near a massive celestial body or a black hole, will experience time passing even more slowly relative to their twin remaining in a weaker gravitational field. When the traveling twin returns, they will have aged less than the twin who stayed behind, just as the special relativity core predicts with velocity, but now gravity is also a key player. The effect can be understood visually as the traveling twin's clock coding in the intense curvature of space-time, which makes their experience of time's passage fundamentally different from that of the twin deep in the gravitational well. Einstein's equations show us that the closer you are to a massive object, the more drawn out your experience of time becomes. Near a black hole's event horizon, for instance, time would slow down so dramatically that an outside observer might see someone approaching the horizon freeze in time, never quite crossing it from their perspective. Conversely, the person falling into the black hole would notice nothing unusual locally. They would feel normal, while the outside universe appears to be speeding up. This gravitational time dilation is not just a theoretical curiosity. It has practical consequences. For example, in understanding the behavior of space-time around neutron stars, where gravity is so immense that time dilation effects are significant and crucial for making precise astrophysical measurements. All these examples highlight how gravity and the curvature of space-time are intricately linked to the passage of time. The twin paradox showcases this beautifully because it emphasizes that time is not absolute but flexible, shaped by both velocity and the gravitational landscape. Gravity doesn't just pull objects, it influences the very tick of the cosmic clock, making the flow of time a dynamic, relative experience depending on your position in the universe. In this way, the paradox becomes a vivid demonstration of the universe's underlying geometry, where gravity weaves the fabric of space-time and calibrates the rhythm of our existence. Real-world evidence and experiments. In the practical realm of physics, the phenomenon of time dilation has moved beyond theoretical speculation and found confirmation through various sophisticated experiments. Atomic clocks, which are incredibly precise, have been essential tools in revealing how time can stretch or compress depending on relative velocity or gravitational influence. In particular, experiments involving these clocks have offered tangible evidence that supports Einstein's predictions about how time behaves under extreme conditions. For example, satellite-based systems like GPS depend on this understanding. Without accounting for relativistic effects, navigation data would quickly become inaccurate. The clocks on board GPS satellites experience less gravity than clocks on Earth's surface, causing them to tick faster by about 45 microseconds per day, an adjustment that, if ignored, would result in position errors of several kilometers each day. Further experiments have pressed these principles into increasingly rigorous testing. In the 1970s, experiments at the National Institute of Standards and Technology involved moving atomic clocks on airplanes or trains to measure time differences after their journeys. Results consistently show that clocks in motion lose time compared to their stationary counterparts, aligning perfectly with special relativity's predictions. These experiments aren't just academic. They serve as direct, real-world proof that moving clocks run slow relative to stationary ones. Advances in technology now permit even more exact measurements, with experiments demonstrating minute time differences at high speeds achievable by spacecraft or aircraft. This has reinforced the understanding that the effects predicted by relativity are real, measurable, and significant for systems operating across different frames of reference. In a broader context, these experiments influence areas ranging from fundamental physics to practical engineering. Scientists regularly test general relativity's influence by placing precise clocks in varying gravitational environments, such as on skyscrapers or in space shuttle missions. The results consistently confirm that gravitational potential affects how quickly clocks run, just as Einstein predicted. For example, experiments involving orbiting satellites have demonstrated that clocks in space run faster than those on Earth due to weaker gravity, further confirming the theory. These findings aren't merely academic. They drive the exact calculations necessary for the functioning of global navigation systems, scientific space missions, and even future explorations of more extreme cosmological phenomena. The accumulation of experimental evidence thus cements the reality of time's fluid nature, moving differently depending on your velocity and position in space. Implications for space travel and future missions. The twin paradox highlights a fascinating reality of our universe. Time is not a universal constant, but is influenced by relative motion. For space travelers venturing beyond Earth's orbit, this has practical implications that are beginning to shape the planning of future missions. If astronauts undertake a journey at speeds approaching light, their onboard clocks would run slower than those remaining on Earth. While current spacecraft can't reach such relativistic speeds, even modest high-velocity travel introduces measurable time dilation effects over extended periods. This raises intriguing possibilities for long-duration missions, especially as propulsion technology advances. Imagine sending astronauts on a mission to a nearby star at a significant fraction of light speed, say 10-20%. Upon return, they might find that Earth has aged decades or even centuries more than they've experienced personally. For mission planning, this necessitates carefully accounting for time discrepancies, not only for synchronizing communication, but also for managing biological and psychological factors associated with aging and mission duration. While the differences are small at current rocket velocities, future tech, such as theoretical warp drives or ion propulsion, might make relativistic travel feasible. Understanding the twin paradox primes us to prepare for the unpredictable ways time itself could bend during such voyages. This phenomenon also raises questions about the sustainability of human life and societal continuity across different frames of reference. For instance, If a crew experiences only a few years due to relativistic effects, but Earth's timeline continues at a normal pace, how will their families and communities adapt? Practical solutions might involve advanced life support systems and virtual environments to mitigate the psychological toll. Moreover, the twin paradox functions as a natural laboratory for future space agencies to simulate and model the effects of high-speed travel on human physiology and aging. These considerations are not merely theoretical. They influence spacecraft design, mission duration estimates, and even plans for interstellar colonization, where the relativity of time becomes an unavoidable factor. In addition, knowing that time can slow down for astronauts traveling at high velocities opens up new strategic options for interstellar exploration, especially in terms of resource management and mission ethics. If crew members effectively age less during their journey, the potential to extend human presence beyond the solar system becomes somewhat more feasible, despite the immense technological hurdles. It's a reminder that the universe operates on principles that challenge our intuitive understanding, but also offer exciting opportunities for expansion. As humanity pushes closer to the frontier of space, embracing the implications of phenomena like the twin paradox may unlock pathways to understanding our future role in a universe where time itself is a flexible and sometimes manageable resource. Mysteries and misunderstandings surrounding the paradox. The twin paradox has long fascinated scientists and enthusiasts alike because it exemplifies how relative motion fundamentally alters perceptions of time. At its core, relativity posits that time isn't absolute, but instead flows at different rates depending on your velocity relative to another observer. Interestingly, many misunderstandings arise from oversimplifications or intuitive misjudgments about what this means in practice. It's a common belief that the traveler's clock should simply run slower in a straightforward way, but reality is more nuanced and hinges on the idea that acceleration and deceleration, changes in the traveler's frame of reference, play critical roles. This is where many get tangled up, confusing effects that are symmetric in theory with the asymmetric outcomes observed in the paradox. Visualizing time dilation can be complex, especially because it clashes with everyday experiences rooted in the idea that time is universally fixed. When an astronaut zips away from Earth at speeds approaching the speed of light, their onboard clock ticks more slowly compared to someone remaining on Earth. However, from the astronaut's perspective, it's the Earth that's moving, so why doesn't the astronaut see Earth's clock as ticking slower? The key misunderstanding lies in ignoring that the astronaut's journey involves a turnaround, an acceleration phase that breaks the symmetry of their motion relative to Earth. This isn't just a technical detail. It's fundamental to why the traveling twin ages less upon reunion. The paradox becomes a puzzle only when one forgets that the traveling twin's frame of reference isn't inertial during the entire trip, a point often glossed over in simplified explanations. The real confusion also stems from how people instinctively interpret relative motion. In everyday life, motion feels absolute. If you sit still, you're not moving. If you walk, you move relative to the ground. But at relativistic speeds, motion becomes purely relative, with no absolute frame of reference. That leads many to think that each twin's experience should be symmetrical, with each twin seeing the other's clock as running slow. Yet, paradoxically, only one twin ages less after reuniting. This paradox is resolved when considering that the traveling twins' change in velocity constitutes a change in their frame of reference, involving acceleration that the stay-at-home twin does not experience. Many misunderstand this key point, leading to misconceptions that the paradox implies a contradiction or violates the principles of relativity, a misconception that persists unless the role of acceleration is clearly explained. Further confusion often arises from attempting to interpret the paradox as a kind of time travel or claiming that it suggests some hidden violation of causality. Some think it means time can be bending or warping in a mystical sense rather than understanding it as a consequence of the geometry of space-time as explained by Einstein's theory. Clarifying that the difference in aging is a real, measurable effect rooted in proper time. The actual time experienced along an object's world line helps demystify this. Proper time remains invariant and is the key to understanding the asymmetry. Yet, because the math behind space-time intervals and Lorentz transformations can seem abstract, many believe the outcome is some kind of strange loophole or paradox, rather than a natural outcome of relativistic physics. These misconceptions tend to fade once the full picture of acceleration, non-inertial frames, and space-time geometry is understood. Ultimately, the twin paradox isn't a true paradox at all. It's a puzzle rooted in our intuitive assumptions about time and motion. The misunderstandings often come from oversimplified descriptions or from ignoring the technical nuances of special relativity. When these are clarified, especially the role of non-inertial motion, the seeming contradictions disappear. It's a story about how our everyday notions of absolute time do not hold up at high velocities. Instead, they give way to a universe where time itself bends and stretches, revealing the elegant and mind-expanding fabric of space-time. The broader significance of relativity in science. Relativity challenges the very foundation of how we perceive space and time, revealing that both are not absolute entities, but interconnected and flexible. At its core, Einstein's theory of relativity, especially special relativity, demonstrates that measurements of time and distance depend heavily on the observer's frame of reference. This may seem abstract, but the real-world implications are profound. For example, atomic clocks placed on jets traveling at high speeds run slightly slower than identical clocks kept stationary, an effect known as time dilation. These differences, though tiny, are measurable and consistent, validating Einstein's insights and transforming our understanding of the universe's fabric. Understanding the implications of relativity has paved the way for technological advancements integral to daily life. Global positioning systems, GPS, for instance, require corrections for both special and general relativity. Satellites orbiting the Earth experience weaker gravity and move at high velocities relative to ground-based receivers. Without accounting for these effects, the positional data would quickly become inaccurate, causing navigation errors that could span hundreds of meters. This intersection of theoretical physics and practical engineering underscores how Einstein's ideas go beyond philosophical musings. They shape essential tools used throughout the world. Moreover, relativity's broader significance stretches into the realm of cosmology, black hole physics, and the general understanding of the universe's origins. It helps scientists decode phenomena such as gravitational waves, ripples in space-time caused by cataclysmic cosmic events, and the expansion of the universe itself. When scientists detect these waves or observe gravitational lensing where massive objects bend light, they effectively confirm that gravity is not just a force, but a curvature of space-time itself. This perspective has opened new frontiers in exploring distant galaxies, understanding dark matter, and probing the universe's earliest moments, demonstrating that relativity remains a cornerstone of modern physics and cosmology. Finally, the broader significance of relativity also lies in how it influences ongoing scientific inquiry and innovation. As physicists attempt to unify general relativity with quantum mechanics, new theories such as string theory or quantum gravity emerge, striving to reconcile the macroscopic and microscopic descriptions of reality. These pursuits often draw directly from Einstein's revolutionary insights, exemplifying how foundational concepts in relativity continue to inspire questions about the universe's ultimate nature. In essence, relativity is not just a theory about moving objects or warped space-time. It's a lens through which scientists examine everything from subatomic particles to the vast cosmos, shaping contemporary science in durable and unexpected ways. The future of time travel and space exploration. Advancements in understanding the fabric of space-time and the principles of relativity have set the stage for a future where time travel and space exploration are no longer purely theoretical pursuits. The twin paradox, a fascinating consequence of Einstein's special theory of relativity, demonstrates that time moves differently for objects traveling at speeds approaching that of light. In practical terms, if astronauts were to embark on a journey aboard a spaceship traveling near light speed, they would age more slowly relative to people on Earth. This isn't just science fiction. It's grounded in real physics that we are beginning to manipulate. One of the exciting prospects is the possibility of using relativistic travel to extend human reach deep into the universe without waiting centuries or millennia. Imagine spacecraft capable of traveling at a significant fraction of light speed, allowing humans to explore distant star systems. The science behind this involves harnessing enormous amounts of energy and developing advanced propulsion systems. Concepts like nuclear pulse drives or potential breakthroughs in antimatter propulsion. As these technologies evolve, the impact on space exploration could be transformative. We could visit exoplanets, study alien ecosystems, and even establish colonies in space, all while only a fraction of the time passes for the travelers. The concept of time dilation could revolutionize not just exploration, but also our understanding of aging and longevity. If space travelers experience less aging thanks to their high-velocity journeys, future missions could last generations, yet feel more like moments. Conversely, the people left behind on Earth would age normally, leading to profound questions about identity and continuity. Advances in quantum mechanics and relativistic physics suggest that manipulating space-time itself might become possible someday, potentially enabling controlled forms of time travel or remote observation of past and future events. Although we're still very far from that reality, current research in space-time engineering hints at a future where the boundaries of time are more fluid than ever. Looking ahead, the integration of relativity into everyday space travel will likely lead to the development of sophisticated navigation and synchronization methods. Precise timekeeping, essential for spacecraft coordination, already uses atomic clocks aboard satellites. Yet understanding and compensating for relativistic effects will become critical as missions push toward faster speeds. Missions to explore black holes, neutron stars, or even wormholes, hypothetical shortcuts through space-time, are conceivable future endeavors that could not only expand our physical horizons, but also deepen our grasp of the universe's ultimate nature. The twin paradox exemplifies the strange, counterintuitive layers of reality that we are on the brink of mastering, transforming science fiction into science fact at an accelerating pace. The core idea behind the twin paradox revolves around the counterintuitive effects of Einstein's theory of special relativity, specifically time dilation. In simple terms, when one twin embarks on a high-speed space journey while the other remains on Earth, the traveling twin ages more slowly than the stay-at-home twin. This phenomenon is rooted in how relative motion affects the measurement of time. Clocks moving at different speeds don't tick at the same rate. As the spacecraft accelerates to a significant fraction of the speed of light, the onboard clock lags behind the clock of the Earthbound twin. When they reunite, the difference in aging becomes apparent, challenging our everyday intuition about time as a universal constant. Imagine a spaceship traveling close to light speed, with the twin on board experiencing only a few years due to the time dilation effect. Meanwhile, from Earth's perspective, much more time passes, perhaps decades. This discrepancy is not a loophole or a paradox in the strict sense, but a natural consequence of how space and time are interconnected in relativity. The key lies in the fact that the traveling twin undergoes acceleration and deceleration during the voyage, breaking the symmetry that exists when both twins are inertial frames. This asymmetry makes the traveling twin's frame non-inertial during the turnaround, which is essential in understanding why the aging process differs. To visualize this, picture two synchronized clocks, one stationed on Earth and restrained to it, and another on the spaceship. The clock on the spaceship, moving at relativistic speeds, appears to run slow from the perspective of an observer on Earth. Conversely, to the traveling twin, the clock on Earth looks like it's ticking more slowly during the voyage. When the spaceship finally lands back, the twin who remains stationary on Earth will have aged significantly more. This effect can be confirmed experimentally using precise atomic clocks flown on jets or satellites, which show slight but measurable differences consistent with relativistic predictions. The twin paradox underscores a profound realization. Time itself is not absolute, but depends on our frame of reference. It illustrates that simultaneity, what one observer considers happening at the same time, shifts depending on motion. The thought experiment highlights that each twin perceives the other's clock differently during the journey. Yet, both perspectives are valid within their frames of reference. The conclusion is that the twins' ages only match when they reunite because the traveling twins' experience involves acceleration and changed inertial frames, which the stationary twins' frame does not. This profoundly alters how we understand time, revealing it as a flexible, relative dimension rather than an immutable constant universal to all observers. So, to wrap things up, the twin paradox beautifully illustrates how, in Einstein's universe, time isn't an absolute. It's a flexible, bending dimension. When one twin journeys through space at near-light speeds, they age more slowly than the twin who stays home, thanks to time dilation. It's a mind-bending concept, but visuals like clocks ticking at different rates help make it more tangible. This isn't just theoretical physics. It's a reality that impacts technologies like GPS, which must account for these relativistic effects. Feeling like you've just stepped into a sci-fi movie? That's kind of the point. Relativity reminds us how strange and wonderful our universe truly is. If this sparked your curiosity, stay tuned. We've got more mind-blowing insights on space, time, and the universe coming up that will make you see the cosmos in a whole new light. Thanks for watching, and don't forget to subscribe for more explorations into the wonder of physics. Until next time, keep pondering the mysteries of the universe, because the adventure is just beginning.